The selection sort. So the basic idea is we have an array that we're passing to the subarray that we're passing here is the one we need to go search for the lowest element, which is basically I to the end of the list. So we pass that by reference, and all we need to do is look for the smallest one. So I think the, so essentially what I'm saying is, like, if you hand me an empty list, I can't really do anything for you. And then what we'll do is we'll say, like, give me the first element, and then I will go from 1 to a len, and I will basically modify minimum if AI is less than minimum, Oh, right. We want the index. Okay, so do we need to store all this information? I think the answer is yes, but I'm not 100% sure. Keep in mind, the point is we're doing this by hand. I wonder if we should return both things, but I don't think that matters, because all we care about is the index. Yeah, okay. So if you hand me a one element array. Hey, how's it going? If you hand me a one element array, I'll just hand you 0. Anything else will actually go through the list and look for the minimum. We have the outside. Well, enjoy the inside. Then, or assuming you have air conditioning, I guess. So we have the ord instance, so we can do this comparison here. We have the copy thing, which means we can do this and this. And that should be right anyway. Okay, so I think that gets us 184. And then here we need to find the Yep, we are doing Rust these days. So assert equal. Yeah, we're working through this book, this introduction to algorithms book, and it's going pretty well, I think. It took me a while to understand what's it called? Insertion sort? Yeah, that one was kind of hard, because I am dumb. And then these other ones have worked okay. So I think this substitute, or what was this one called? This one's called selection sort. Is that what I called it? Yeah, selection sort. I thought it was called substitute. Okay, anyway, it's a selection because I guess we're looking for the minimum index. Also, thank you for the birthday wishes. Okay, so minimum index of basically an empty list should give you none. Um, you can be. Do I have to do it like this? Doesn't really matter what I give you. So it's probably like. Oh, wait, no. I should be able to use private functions here. Minimum index. Hmm. Maybe I can't do it like this. Maybe I have to go. Okay, let's do it a different way. Okay, there you go. So it must pick like a default type for this vector when we initialize it, so we don't have this problem. Or maybe all I needed to do is do vec like this, and then we're fine. No, it doesn't like that. So anyway, we'll just leave it like this. And then we can cargo test this thing. Oh, and then this doesn't show up in here, so this can be a vec u8. Literally doesn't matter what it is. Okay. I guess we'll just leave that like that. Okay, so now let's like do a real test. So this should turn 0, 1, 2, 3. 3, I think. Yep. Okay. Um and like that's arguably an edge case. 0, 1, and some. Okay. And now we look at this. So we go find the min index. If we're able to get one, then we need to swap the okay, so what if the min index is I? We don't need to do this. So if uh, x not equals I, then we need to swap. Oh, but that's not going to work. It's because we're passing the subarray. Hey, Sitsu. Thanks for the birthday wishes. Yeah, cool. How's it going? So we're just finishing up this min index function. Oh, actually, 183. That's done. This is really like we need to finish this function first. But I think it's either yeah, we're 0 index. So if we start at 0 and we find 0, we don't need to swap. So I'm pretty sure that this is probably right. And then we say like here's the value we need to swap. Is at a sub I, and we're going to put that in let swap index equals x plus I. It's like the subarray index, the subarray to the array index. Like a conversion between these things. So we're swapping I with the sub to our index. Something like this is probably a little easier to write. And this is also sub to our index. And we really own, well, we should do that just so we can make the comparison there. Okay, so we have a looks like a Rust rant potentially. It feels like a language that doesn't know what it wants to be, kind of like C++. Uh, I didn't know about the result part, but I think it is expression based, but yeah, I don't know. Or it is expression based. Like this is kind of like the expression return syntax here. Like obviously I'm kind of short circuiting this here, but I didn't really have to do that. I could have like matched on the length. Yeah, I mean I mostly understood what you meant, but I also don't think it's trying to be Haskell. Like it adds pieces from Haskell, but I don't think it's trying to be like Haskell. I don't think it would want to be that because then like avoid success at all costs and all that. Okay, so anyway, I think we're saying basically here, anytime we enter this loop, we should also be given a subarray, which is like totally reasonable. Um, yeah, that's what I mean. So like it doesn't have monads, so it's like actually frustrating that it isn't more like Haskell because you have the concept and you could have it, but they don't. So maybe that's like a good example of, or a counter example to that thing. Maybe they'll have it someday. I think also, from my understanding, like there's asynchronous stuff, or like one of the goals of this language is to be like fearlessly asynchronous as well, similar to like how Haskell STM can do that as well. But like the APIs are not like there yet, so I don't know. I don't know a lot about this language, but I know that it's worth messing with in my mind. Like maybe I could have done this in C++ or I mean, the other options were other just kind of like boring imperative languages. What's my goal with Rust? It was just that like all of the exercises in this book are going to be geared towards imperative programming, like languages. So having the escape hatch to like have an imperative program means that I don't have to like force force Haskell into looking like maybe the code out experience here. Because like basically they have like pseudo code blocks that are essentially like Python code. Like if you just look at them, you would think they are Python. So that's kind of where we're at. Anyway, so we expand we expand the index. If the index is not our current index, we need to swap, and then we're done. And this thing gets a mutable t, so mutable reference to t. So we should just be able to return the vector. So this is going to be very similar to this one. So let's just copy this whole test. And we'll call this selection sort works. Selection sort should do the exact same thing that it did before. And it does. Okay, so let's make some edge cases. So what if we hand this thing an empty array? Empty array works. I can't say input equals input, obviously. So that should still work. That's kind of a funny statement. Doing Rust when you have already landed a Haskell job is like working out after you've gotten married. So the way I see this is like, I'm not currently concerned about my job at all. But I would also like to be prepared if for some reason like I can't use Haskell anymore. And if I had to pick a language right now that wasn't Haskell, and was imperative, I would probably rather choose Rust over something else. That being said, I'm not concerned about my jobs, so like this is more just something to do while I'm here. And also like exposure to other language. Like it was very clear to me the first day we did this that I do not remember how loop indices work, like at all. And so it's probably good to just keep practicing this stuff and just make sure that I keep those chops up. Another thing is like, let's say, I don't know, again, I'm very happy with my job. I have no interest in leaving currently. But, maybe in 5 years, I want to do something different. I don't know. 5 years is a long ways away. And let's say I go into and have to take like algorithm related job like tests, whatever they like programming interviews. I need to have that, and I need to be able to do that in a language that's conducive to it. Because if I write it in Haskell and then like I can't finish, that's gonna look worse than if I write it in a language I know I can finish in. Um, so, you know, just things to think about. Anyway, so does this work? It does. Um, with one element, it should work too, and that's like um doesn't. I don't think we need to specify a type here. It just picks one automatically. And so if we try to sort this, we should get the output. Cool. So there's selection sort. Is there anything here that we can like make better? I feel like the answer is no, but also I'm not 100% sure. One thing we could do is we can actually remove well it becomes weird. So like we could say that the minimum. Okay, so we could demo this expression syntax and just say if this is 0, right? And we could do the same thing here. Okay, but I don't want to do it this way. I want to do it differently. Because I want to like I want to make this less crappy is my idea. And maybe I can't actually. But the general idea is like, what if we rewrote it this way? Do you normally put these on 2 lines or 1? I'm not sure. I don't think this is like better in any way, but so are we guaranteed to have? If we hit this, we're guaranteed. So I think we just like straight up unwrap this one. And then we would have to wrap these in some. Is this any better? I feel like the answer is no. I'm just trying to think of a different way to write it. I was also thinking about trying to show the like expression syntax a little better, but this really isn't actually conducive to that. Thank you, Script. How's it going? Happy you're here. I think there's probably also some way to say like unwrap or panic. Or like unwrap or I don't know, return none. Let's see if we can find something like that. Although maybe that's like weird behavior. This no. That's not gonna help me. Anyway, I don't know. We could also put this thing into a sum, but that's like another. Like that's probably fine too. Anyway, see if it still works. It does. So I don't know. Just another option. Is it better? I don't think so. I think they're both fine. I would argue people who aren't familiar with sum would find this harder to read than the other one. What do you think? Anyway, okay, cool. So I think that's it. It actually told us to write the pseudocode, but we wrote like the actual code. I think that's fine. And then it asks some questions here about a few things. So this was, where's my slash? There it is. This is exercise 2.2-2. So, okay, so loop invariance. So basically, I think the loop invariant is that selection sort of A0 to I is the same as A0 to I, right? So it's like given any subarray, it should be sorted. It's similar to the insertion sort one. And I would guess that like almost every sorting algorithm is that way. Maybe that's not true. Maybe there are some where the loop invariants are slightly different and that's what makes them like optimal for some reason. But I would think that this is the loop invariant that we're trying to preserve. Yep. Okay, and then it says oh, that's a good point. Technically this can be a length minus 1, right? And everything should still work. Oh, well. Oh, because the length is 0. Okay, so it's failing on an empty array if I do this. Because basically if we have an empty array, there's nothing to do. So we do need this here, otherwise like I suppose we could say just as a guard against that, if a len is 0, there's nothing to do, just return. And then you could put this here. Yeah. So this just prevents us from having to do the like let me just show the example. So if we don't do it this way, then this selection sort has to sort this last element. So it's going to end up in a situation where what will we have? Well, just pretend we had a sorted array, because it's probably easier. So if we tried to selection sort this one, it would say, here's a 6. Now go to see if 6 is the minimum value. It is the minimum value. Don't swap. But we don't need to do that because we've already put, we would have already have put the 6 in the right position because we don't need to do the last element. So, yeah. Anyway, this is like a slightly weird optimization. Well, it's not a weird one. It's just like that's how the only way you can do it in Rust because you can't say a-1 for a U size. This allows us to write a.len -1 below. And the algorithm still works for an empty list. Why is that so? That's too many characters. I assume that's like something we can edit. Anyway, that's fine. Okay, cool. So there's selection sort. We did the loop invariance. We discussed why we can do it for the first n-1 elements. And then it says give the worst case running time for selection sort in theta notation. Is the best case running time any better? Okay, so now is where we need to pull out probably a this notebook. Okay, so one thing I'm gonna do this weekend is I'm gonna move the microphone over like here. So it's gonna sit here and it's gonna be on this side of the desk because it's like I don't have really access to this whole thing, this whole part of the desk, because as soon as I look over here, there's a big fat microphone. So like I have all this space over here and I can't use it because of where my microphone is. So I haven't figured out what the best place to put a microphone is yet. I've moved it a few times. Anyway. Okay. So we need to do RM view. And tell us. The desk is sufficiently wide on the right side. So like I have my work laptop on the left side, my mouse on the left side, and like some other stuff over here. But on the right side I have like this big empty open desk, so it's just using that. What did we do today? We wrote selection sort. We finished selection sort. We found some bugs in our original implementation, and we wrote minimum index in probably arguably a weird way, but I don't know. I wrote it. I wanted to see if I could clean it up, and I couldn't. So that's just what we ended up with. And we discussed what loop invariance this maintains, and now we are, which it's the same exact loop invariant that's maintained for the insertion sort. And now we're trying to do theta notation for the worst case. So what's the worst case? Is it just reverse? Let's see. So I'm just gonna like so in this case you have to swap 6 1 5 2 4 3. That doesn't seem so bad. Um, don't swap, don't swap, don't swap, don't swap, don't swap, don't swap. I feel like all the cases are sufficiently complex. Like they're all the same complexity essentially. From a number of loops standpoint. Because you have to go through the whole list no matter what. And each time you have to go through like this subarray and find the minimum. You know what I mean? So I think the loop complexity doesn't change in the worst case or the best case. Is that right? I feel like that's right. Yeah. Um there's no way for you to have a best or worst case. They're all the same. And so let's think about the theta notation business. So do I want to try and assign how many times we do everything to each line of code? That's probably what I want to do. And then basically just find the worst piece of code. Okay, so this loop is always going to run so I think line 207 is always going to run like something like how they write it here anyway. Sum I equals 0 n t sub I, where what was t sub I? T sub I was like the runtime for the loop. And then every time we hit this line, we have to run L208 sum I equals n, or not n, I guess. I'll just write j to n, t sub j or something. So, like, this is n. I don't think we've seen one like this before, right? Well, I guess it's not quite the same as the insertion sort one. But my feeling is that there's a log in here. But really, I haven't thought about logs in a while. And the reason I think it's a log is that this j decreases each time. But like, is that n log n? Is it? I don't really remember that. Are there solutions to these? That was one thing I actually haven't looked at yet. We haven't really needed them. So just checking to see if the... Holy cow, there's a ton of citations. Okay, so problems. I don't think there's solutions in the book. Unless they're prior to... They have Appendix C. Oh, I should just look at the index, huh? Okay, so they have basically a mathematical algorithm and an index. So there are no solutions to the problems. Um, so I think we just have to kind of guess. Oh, that's a good point. But we probably have to. Let's see. We probably have to buy it. Instructor. Okay. So let's grab this and put it in the README. It may not have the solution. Okay, so we're looking for 2-2. 2.2-2. Okay, cool. Okay, so we got that part right. ON squared for all cases. Oh, right, because this thing. Wait, but it's not really. Is it n squared? It feels like not n squared, but also I don't really have like an intuition for this here. Because it doesn't feel like you have to go through the whole loop. It feels like an n times something. Maybe it's not log, so that's why it's n squared. I wish there was more like notation here. Does anyone have any intuition about this? Like, why is it? It feels like it's. Oh, is it because it's n times n minus 1 or something? And then that just ends up being n squared? Well, it's not n times n minus 1, but. Write the explicit sum for small cases. Like, each loop is n times n minus 1. But it's kind of not. My phone is blowing up right now. Okay, so let's see if we can get this figured out. Okay, so like, yeah, it's not really n times n minus 1, right? So like the first, okay, so let's say we do loop 0, right? We have to do the first loop n times, and then the second loop n minus 1 times. If we do loop 1, we're, oh wait. Oh, so maybe that's as simple as it is. Because all that really matters is the first loop. That's the worst case, which is why it's n times n minus 1. And then that's just essentially n squared minus n, which is just n squared. Is that all I have to do? Am I overcomplicating it? Well, this is like, I feel like maybe I'm simplifying it here. That's what I'm concerned about. I don't know. I'll see if somebody says yes, but I feel like this is like the sort of the worst case is the first loop. Girth Day. Thank you. Okay, so my logic here is in the worst loop, you have your outer loop, you have to do n times, and then your inner loop, you have to do n minus 1. And technically, it's n minus 1 for the outer loop as well. And then you would distribute these, and you would end up with, what, n squared minus 2n plus 2? But none of this matters in theta notation, so you just end up with theta n squared. Is that better? So technically this is n minus 2, I guess, but you get the point. Yeah, but the last iteration doesn't matter, right? It's just the worst case that matters. For theta notation, if I understand theta notation correctly. Maybe I don't. I definitely don't. This changes the math a little bit. Oh, actually, no, it doesn't. Yes, it does. I feel like I don't understand how to evaluate the inner loops. Like the outer loop is always n minus 1, and then their inner loop is not dependent on n. It also depends on I. It's like I minus n. Yeah, that's what I'm worried about. And it just happens to be that because I wrote it in this way, I'm getting this. So like the inner complexity in this case is like, let's say this is I. It's like n minus I minus 1. That still works because we have to go. And I also think that it's really not minus 1 because we do have to go to the end here. So I think it's something like this. And so each loop, the inner one is n minus I. And that's where you get the double factor of n. This is why I don't like when they don't explain these things, because like it's not intuitive to me how to do this typically. And this is where I get really stuck when I think about algorithms. And I don't really have a professor to ask at the moment. Anyway, I can look this up too, so, or ask around. So, my feeling is the runtime is something like n minus 1 times n minus I, which is just theta n squared. Try to count exactly I just don't see how it's n squared. I feel like it's not, but I also have no ability to do this. Right, this is where the n-1 term comes in. That's very clear. And then if we go up here, this is not n, right? Like, this is a subarray. Maybe it's the pseudocode that they wrote? No, because it's I plus 1 to n, which is what I'm writing. How many times do we reach 187? Yeah, that's what I'm saying. Like, you reach 187 n minus 1, n minus I times for whatever the inner index is. You don't hit this n times because the a that we're passing here is not the total. It's like whatever's left, right? And whatever's left is shrinking each time. And even with the pseudocode they show, that's true, right? Okay. Let's see if there's something here. Okay, let's look at this. So the Gauss summation. Ah, yes. Johann Carl Friedrich Gauss. Yep. Okay. So a legend suggests. Okay. Mm-hmm. I don't understand. What trick? Why does this trick matter? This is an interesting trick. Oh, here's the trick. The number of pairs would be this number divided by 2. Mm-hmm. Oh, the explicit sum? I don't know. Okay, so if we think, okay, so basically inner loop of minimum, can't spell, minimum index. Is going to be sum I equals 0 to n minus 1 sum j equals I to n t sub I, right? However long the inner thing takes. And that's why I was writing, that's kind of like why I was writing n minus 1 times n minus I. But t sub I is less than a constant. Yes, yeah, like the actual value of t sub I basically doesn't matter. So the inner sum is less than constant times the inner sum is less than, okay, so we're saying that this is sum, wait, yes, that's what I said. Right, like it's less than C1 times n minus I. And then this whole thing is n minus 1, which is why I was thinking n times n minus 1. Or n minus I. Maybe I'm confused where you're going with this. Like it's still n squared. Like in theta notation, it's still n squared. But like it feels, I think it's still that way. But it just feels weird because it's not really, it doesn't feel like it is exactly n squared to me. Like it feels like it's less than n squared, but I also don't know how to simplify the solution very well. Like it might be just that this, because this is still linear in n, right? Like this is, maybe that's the right way to say it. Like it's still linear in n. We're not like somehow logarithmically reducing the input. So it's essentially just n. And this is also linear in n. So it's n squared. Anyway, I think it's probably fine. Okay. It says consider linear search again. What was linear search? 214. 214. Okay, so a sequence of n numbers stored in an array, an index I such that x equals a sub I. Oh, it's just like, okay, it's just a like literally search for a number, which I think we wrote before. So consider that how many elements of the input array need to be checked on the average, assuming that the element being searched for is equally likely to be an element in the array. Okay, so to exercise 2.2-3. So if we have A, which is a vector, A sub 0, A1, AN, whoops. And an X is just a value, like find I where A sub I equals X. Okay, so that's the problem. And then it says, okay, so the worst case is I equals N. Okay, and then on average, if they're equally likely, so I haven't really thought about statistics very recently, but right, so if I remember how to do this, it's like P times N. How do you do statistics? I don't remember. Okay, let's do it this way. So if we have like 3, then this is equally likely. So um, you have like N over 3. N over 3 chance that this thing is uh but this is now, is this how this works? Gosh, I haven't thought about statistics in a long time. Okay, so it's like the chances is N here, and then N minus 1. I feel like this is wrong. There's some way to do this, but I don't remember. I gotta look this up. I'm sorry. Um, so there's something to figure out the average case. We just need like some statistical representation of this. But I think in theta notation, it's just theta n because um, like the worst case is you have to search the whole list. So it's theta n. And I would guess that the average case is probably just n over 2. Like, you know, if you just randomly if you randomly sorted like 1,000 lists of the same length, uh the and then randomly chose like an X, you would end up there, I guess, right in the middle. But I don't know how to do that in mathematics, so or I don't remember how to do that. Okay, last thing, 22-4. How can you modify any sorting algorithm to have a good best case running time? Oh, that's a good idea. We could go through some of the probability stuff. Very good point. I literally looked at it a minute ago. How can you modify any sorting algorithm to have a good best case running time? I feel like this is a trick question. I don't think you can just I always overthink these questions, but like if you stop maintaining your loop invariant and just return the array, then it always has a good one. But that doesn't preserve the best case running time. I don't really understand the question. You could check if it's sorted and then return it if it is sorted. But that would change the worst case running time. But I guess that's not the question. So I think that's what it means. I think that's what it's looking for. If you just check that the array is sorted. If it's sorted, return it. That's how you could improve the best case running time. It doesn't say anything about the converse of that. Like you're not paying penalties for that. So I think that's that. Okay. So I think that's it for section 2.2. But I think maybe we should spend a little time with the statistics stuff, since I haven't looked at it in a while. But I need to go to work, so